Okay, so we have equation 4.16, right? And what is equation 4.16? It's basically the second term in equation 4.15, okay? And we have written it as a difference of two terms. There's a negative sign here. Okay, but look at that first term on the right-hand side. It vanishes. It goes to zero because remember, eta was defined to be equal to zero at x1 and at x2. So this first term goes to zero. Okay, second term is still there. So the second term of equation 4.15 just gets replaced with the second term of equation 4.16. And you'll notice both the first term is proportional to eta of x. The second term is also proportional to eta. So we can combine the two terms again into a single integral and factor out the eta. And this is what we get. And we have our derivative, right, which is now an integral with this form. The integrand is these two terms, both multiplied by eta, and then we integrate from x1 to x2. Okay, so now what do we want to do? We want to take the derivative, di by d epsilon, and set it equal to zero. So we say this is equal to zero when epsilon is equal to zero, because when epsilon is equal to zero, big Y is equal to little y. That's the function we're looking for. Okay, so set this equal to zero at epsilon equals zero, but when epsilon is equal to zero, you can just replace big Y, and therefore big Y primed also with little y, and little y primed because of this condition here. At epsilon equals zero, big Y is equal to little y. So we have this equation here, this integral is equal to zero. Now, the thing to remember is eta was completely arbitrary. Other than this condition here, that it vanished at x1 and x2, it is completely arbitrary. The only way that this integral will always be equal to zero, regardless of what arbitrary function you put here for eta, is if everything in the square brackets, the first factor, is equal to zero. And this is it. This is the Euler equation. Setting that equal to zero gives us a differential equation. This is the Euler equation. And what this equation is going to do is to set up a differential equation for the unknown function y. And remember, the unknown function y is the function that minimizes or maximizes an integral of a certain form. It will minimize or maximize. Let's go right back. This integral. Okay? So in a typical problem, you're given this integrand. Okay? You are given it, or you can, with other information, determine what that is. And then you want to find the unknown function y, which minimizes or maximizes this integral between specifically chosen points x1 and x2. Okay, so you know what the two endpoints of the integral over x are. Okay, so what we have done is we have done the following. We've started with one problem and replaced it with a different problem. Both of these problems have the same solution. So if I can solve the differential equation that emerges from the Euler equation for the unknown function y, I will have also found the function which minimizes or maximizes that integral that was shown a few slides back. Okay, now all of this is going to seem a little bit unclear until we actually go through a problem. So let's go through one problem. Let's go back to the geodesic problem. So remember, we said that if you want to calculate the length of a curve described by a function between x1 and x2. That can be written as an integral. The integral with respect to x between x1 and x2 of the square root of 1 plus the square of y primed. So what we have here is a problem where, remember we talked about in the derivation of the Euler equation, the function big F? Big F here is simply this, the square root of 1 plus the square of y primed. In this particular case, this integrand does not depend explicitly on x, and it does not depend explicitly on y, though it does depend explicitly on y primed. So it's a simple special case where it only depends on one of these three quantities. Okay, and big F is clearly the square root of 1 plus y primed squared. Okay, so we're going to do what? We're going to use the Euler equation. There's the Euler equation. So what I need to do is to take the derivative of big F with respect to y, treating y as a variable. Also take the derivative big F with respect to y primed. And that we will also take the derivative with respect to x. Okay. So let's take a look here. So big F looks like this. So if you take the derivative of big F with respect to y primed, you can do this derivative yourself. When you treat y primed as a variable, you get y primed divided by the square root of 1 plus y primed squared. Okay? Again, you're just treating y primed as though it were a variable like x. The derivative df by dy, well, there is no y here, so the derivative is 0. If you substitute both of these derivatives back into equation 4.19, okay, the second term is equal to 0, and we have the derivative d by dx of this partial derivative, df by dy primed, okay, and that says that we have d by dx of this expression here, y primed over this square root, is equal to 0. Okay, now you can go ahead and take the derivative of all of this stuff and complicate things, but you know what? Just to keep it simple, let's not do that. If this derivative with respect to x is equal to 0, then obviously the quantity, the expression you're taking the derivative of, must be a constant. Okay, so c is a constant. Okay? If c is a constant, then look, you can solve this equation, you can solve y prime for y primed in terms of c. Okay, I haven't written it out, but you could square both sides, so you would have y primed squared, and then the same expression in the denominator without the square root. You have c squared on the other side. Multiply by the denominator both sides. You get a quadratic equation for y primed. You can solve for y primed in terms of c. All you're going to find is that y primed is also just a constant. Okay? If this expression is a constant, then y primed itself is equal to a constant. Again, if you don't believe me, square both sides, construct the quadratic equation, and solve for y primed. You'll see it just depends on the constant c, therefore it's constant. So let's call this constant, not this constant, but let's call the constant that is y primed, let's call that m. Okay? So we have, therefore, y primed, which is dy by dx, is equal to m. Well, you can integrate that easily enough, and you find that y is equal to mx plus a second constant, call it b. And lo and behold, what you see is a straight line. This, is, of course, is the equation for a straight line between 2 points, is the function which will give you the shortest path between the 2 points. That seems kind of obvious. Well, it is obvious, but this is a simple special case, a simple illustration of how to use the Euler equation. And we know what the answer is, so we have clearly done it right. Okay. If you want to know what these two constants are, well, then you can go back to this. You say, well, I know that between point 1 and point 2, we have a straight line, which is the minimum distance between the 2 points. Well, how do you get the 2 unknown constants? You'll use information about the 2 points that you know lie on the curve. From x1, y1, x2, y2, you can get the slope and the intercept of the straight line that goes through those 2 points. You might ask, well, how do I know where did we show that this was going to be a minimum distance as opposed to a maximum distance? And the answer is, well, we haven't shown that explicitly, and we're not going to do that. But in this case, this clearly represents the minimum distance. Okay, so you can come up with similar kinds of problems, which are less trivial. For example, let's say you have a curved surface and 2 points lie on the curved surface, and you want to know the trajectory along that curved surface. That's the shortest trajectory connecting those 2 points. The surface could be something like a sphere or a cylinder or something even more complicated. Okay, so geodesics, it turns out, are important in the context of relativity. And there's one problem, the last problem on your very last problem assignment, that deals with this matter. So it turns out that in relativity, you can think of objects moving along geodesics, but not geodesics through space alone, but geodesics through space-time. So you kind of think of space-time as a 4-dimensional space. 3 of the dimensions are spatial, x, y, and z, and the 4th dimension is essentially time. So there's a quantity that connects 2 events with, okay, remember from relativity, an event, to specify an event, you specify the position, that would be x, y, and z, and time, okay, so position and time. And if I have two events that are infinitesimally close to each other, dx, dy, and dz represent the 3 displacements in the 3 different directions, and the time between the 2 events is dt, we define something called a space-time interval. I say distance, it's not really a distance. It's something else, okay? And in so-called flat space-time, this space-time interval is minus c squared dt squared plus dx squared plus dy squared plus dz squared, okay? C is the speed of light. What the physical meaning of this is, this ds squared quantity is not clear. Don't try to demand that it have a physical interpretation, okay? We simply call it the space-time interval. It's kind of like a distance, but it's not really. And note that negative. The negative sign is important, okay? So the trajectory of a particle that goes between points 1 and point 2, well, point 1 and point 2, I mean you have to specify both the time and the position for point 1 and point 2, event number 1 and event number 2. It turns out that objects will spontaneously want to go along a trajectory between 2 events that maximizes this integral. Okay, point 1 to point 2, you're specifying the time and the position for point 1 and point 2. It's the square root of negative ds squared, which looks strange. Are we taking the square root of a negative number? No, okay, because these 2 events are time-like in nature, and that means that ds squared is always going to be negative, and it turns out that that will be true if the 2 events correspond to a given time and position for some one object.